Hi everyone. So in last video in a logistic regression lecture series, we basically explained that the relationship between the Bayes theorem and the logistic regression model and other classification techniques. That means what? If you have this Bayes theorem and if you are going to model this class condition probability directly, that means you are going to use the discriminant analysis. But if you want to if you are going to model this posterior distribution directly, that means you are going to use the logistic regression. So now we are going to talk from that onwards. So in logistic regression, as I mentioned you previously, we model this posterior probability directly. So that means what? So usually in classification we can classify for more than two classes, but in logistic regression we are basically the most popular technique is that we use logistic regression only for two classes, but if you want, you can generalize this method to predict more than two classes as well. So since we are interested in two classes, so that means the y has only two levels. So because of that, we can tell y has a Bernoulli distribution with probability p, that is a parameter of the Bernoulli distribution. So here basically we are modeling this parameter p because that is the unknown factor of this. So this p means what? The probability when y is equal to 1, because there are only two classes. So we are going to model this probability p as that we are going to model this p as the probability when y is equal to 1, that is the expected value of y. So in more general terms, we are going to model this px, that means the posterior probability px, that is equal to what? For a given set of predictors, what is the probability that particular observation belongs to first class? That means the probability that y is equal to 1 given the observations. Okay, so that means what? We are basically finding the mean function, that means the expected value of y for a given number of predictors. Okay, so this is called the mean function. This expected value of y given x, we call it as a given function. So if you recall the linear regression, in there also we are finding a mean function. That means we are going to model this expectation of y given x. So here, like in linear regression model, we are going to model the mean function. That means this expectation of y given x. So that means in linear regression model, we directly use this relationship. That means expectation of y given x is equal to x transpose beta. So my question is that can we use that method in here also? That means in order to fit or in order to model this logistic regression probabilities, can we fit this same model for this data as well? So if you think about a bit like that, then you will see the answer is no. Because why? Because in right hand side of this equation, if you consider right hand side of this equation, it can be any value, right? This x transpose beta can be any value because there is no restriction. But if you consider the data here, we are actually estimating a probability because this p of x is a probability. So this p of x, that means in other words expected value of y given x, in this particular example, what? It's a probability. So it can be always between 0 and 1. So if you directly use this model, then what will happen? The left hand side of this equation will be a value which is between 0 and 1, but the right hand side will be an any value. So that is not good, right? So that is a problem if you use this model directly. So what you are going to do? So what you are going to do is, instead of directly using expectation of y given x is equal to x transpose beta, we are going to use a function of expectation of y given x transpose beta like this, so that what will happen is this function of expectation of y given x can be any value. So by doing this kind of a transformation for data, so we convert this left hand side of this equation in a such a way that this g of expectation of y given x can be any value. So this g is called as what? This g is called as the link function. This g we call it as the link function. So when you consider the linear regression, in linear regression it is like expectation of y given x is equal to x transpose beta. So in that case, in linear regression, this g is an identity function. Okay, so this link function for linear regression is the identity function. So now we have to find such a function for logistic regression as well. So the most suitable function in this case is what? The most suitable function is in logistic regression is logit function. They choose the link function for logistic regression as logistic function because it has some advantages over other choices. So okay, so now we are going to model this p of x in logistic regression. We are going to model this p of x in logistic regression based on the logit link function. So what is the meaning of this logit link function? This logit means what? A logit of a particular function is equal to what? The log of the odds ratio. That means log of the p of x divided by 1 minus p of x. This p of x divided by 1 minus p of x, we call it as the odd ratio. So this logit of px means basically the log of the odds ratio. Okay. So now we are going to equate this logit of p of x is equal to x transpose beta. Okay. So that means what? If you, so this means what? This will be equal to log of p of x divided by 1 minus p of x. So in order to find the p of x, that means the posterior distribution, what you can do is you can take the exponent in both sides. So if you take exponential in both sides, you can derive this equation p of x is equal to exponential x transpose beta divided by 1 plus exponential x transpose beta. So this is the logistic function. So this is the one advantage of using logit as the link function in logistic regression, because of that we can derive something we can usually interpret, because this logistic function is a probability density function which is between 0 and 1. So that is one advantage of using logit function as our link function for logistic distribution. So now I am going to talk about how to interpret the regression coefficients in logistic regression. So the first case that I am going to talk in this video is in a situation there is only one continuous predictor. That means there is a one predictor where it is a continuous variable. So in that case we can have this relationship. the relationship is what? The log of px divided by 1 minus px. That means the logit of px is equal to x transpose beta. In other words, the right hand side is equal to what? Since there is only one linear predictor, it will be equal to beta naught plus beta 1 x. Okay. So in this section, I am going to because some might have heard that the interpretation of beta is something like the exponential beta is equal to odds ratio. So here I am going to derive that relationship. Okay. So if you have something like this, so what does this mean? So let's say this is a y. That means in simple linear regression we call it as what? The beta 1 is what? The change in logit when x is increases by 1 unit. That is in simple terms. Okay. But here this y is what? It's a logit of px. Okay. So that means what? This x increases by 1 unit means we can write the same thing as follows. The beta 1 is equal to what? Beta naught plus beta 1 times x plus 1 minus beta naught minus beta 1 of times x. So this is the same thing as what? The change of logit when x is increases by 1 unit. You can write the same thing as follows. So this means what? So this thing is equal to what? The logit or the log of what? P of x plus 1 divided by 1 minus p of x plus 1. That means the logit when logit of what? The p of x plus 1. And this thing is equal to what? The log of p of x divided by the log of 1 minus p of x. So in other words, this is equal to what? This is the log of new odds minus the log of old odds. Okay. So that means what? Since you have a subtraction that involves log, you can write it as a division like this: log of new odds divided by log of new odds divided by old odds. So this is, in other words, we call it as the log of odd ratios. Okay. So because of that, we can write beta 1 is equal to logs of odds ratio. Okay. So when you take the exponents of both sides, then what will happen? Then odds ratio is equal to exponents of beta 1. So that is why in practical situations, when we are interpreting the coefficients in logistic regression, we are talking about this odds ratio, because this odds ratio is coming from this proof. So basically the exponent of beta 1 is equal to odds of odds ratio. So that is it for this video. So in next video I am going to explain in a situation where this x is a categorical predictor, because in this case x is a continuous predictor. Okay. And I am going to explain that with some examples as well. So if you think this video is useful to you, just put a like on my video, and also if you want to see more videos like this in future, please subscribe my YouTube channel. Thank you.